one of the things that we talked about at the very end of last time was parameterizing a sphere. And so let's talk about parameterizing a sphere, and then we'll try to generalize to other things. So when you parameterize a sphere, the most familiar equation that we have for a sphere is in Cartesian coordinates. So we can start with this. Now, if you're parameterizing the whole sphere, then doing things in Cartesian coordinates might not be the best way to do this, but we can kind of get started and think about this. And so I'm going to label this as a graph parameterization. To say that I'm going to use this Cartesian coordinate equation to parameterize it. And what I'll do is I'll use x and y's, and then I'll have you think about how to change this into u's and v's. So the graph parameterization for this would be x equals x, y equals y, and z equal to, now you're going to need to solve for z here. It's going to be the square root of 1 minus x squared minus y squared. So this would be what's called the graph parameterization. And we saw that when we tried to graph this, so if you don't have a fancy graphing program, I would suggest that you click on this link, and this is somewhere on our website, and it's free, except you have to make sure you have the updated version of Java. One of the first things you should do is you should click on this so that you can make this graph disappear, and by clicking on that you're essentially unchecking it, because we don't want to see that graph. That's just some example. And then we go to this thing called graph, and we ask it to graph as a parametric surface. And that's going to open a new pop-up window, and the pop-up window has an example that you can graph and see how it looks like. But if you know what you want to graph, then you're going to graph what you want to graph. So remember that a lot of programs use either u's and v's or s and t's to graph surfaces. And so if I have this in terms of x and y, I just should find the appropriate substitution. I'll let x equal to u and y equal to v. And so this is going to be the square root of 1 minus u squared minus v squared. And if we're talking about this as a unit circle, it has radius 1. So I can see this coming from minus 1 to 1, and then minus 1 to 1. And if I graph it, remember the graph had this funny edge to it. That's because our limits are constant limits, and whenever you have constant limits, that's usually describing a rectangular region. So when we take a look at this, I'll put this a little bit lower because I want to add something else to that. This uses a rectangular region from minus 1 to 1. And so what we want to do is we want to shave that off a little bit, and we want to look at it so that straight from the top we want it circular. And in order to do that, we need to explain to our grapher, this particular grapher can't do it, but we have to explain to whoever's graphing this that our domain has to describe a circular region. Okay, a circle of radius 1 goes from negative 1 minus x squared, the y value, and then positive 1 minus x squared. And then the x values go from negative 1 to 1. So we're parameterizing this. In terms of parameterizing, we're kind of looking at this as a double integral, where we're trying to find out what's happening on the domain. And in your domain, if you restrict your domain to be just a circle like this, then you're going to be in pretty good shape. Okay? So this is your graph parameterization version of this. Now, remember that this is only the top. And so if we want the bottom, to get the bottom, you have to let z equal to the negative of this original z function that you have, and then now you can include the bottom. So you'll still need to break this up to two pieces. Yeah?
How did you get the y bounds?
The y bounds? Oh, I just have to describe this thing. The domain has to be a circle. Circle of radius 1, x squared plus y squared is equal to 1. So, yeah. Okay? All right, so that's one type of graph, the graph parameterization. We also know how to do this thing in spherical coordinates, or cylindrical. Let's do cylindrical first. I don't know why, but because spherical is really the best way to do this. But just to show you that you can do this in cylindrical. In cylindrical coordinates, you would let x equal to r cosine theta and y equal to r sine theta. And then z is equal to, well, it's like this thing, except instead of x and y's, you have r's and thetas. So you still have not only a complicated, slightly complicated z, but you also need to take a look at the top and the bottom half of this. So that didn't solve our problem with the top and the bottom half business. And so for us to be able to deal with that, we're going to go into spherical. But at least your limits now can be constants. That's at least a nice step in the right direction. And if we pull out our graphing calculator again, in cylindrical coordinates, I would just need to translate this in terms of u's and v's. So maybe I'll let r equal to u. So this is u times cosine v, u times sine v, and then still the square root of 1 minus u squared, if u is equal to r. And I need to make my adjustments with the limits now. Now I have constant limits from 0 to 1, and then constant limits from 0 to 2 pi. So now I'm able to get rid of that little bit in the bottom. And remember, the more partitions you have, the better it's going to look like. So if I have 3 partitions, this is not going to look very good at all, because I'm only taking 3 steps along my theta. I think if I took 5 steps, it looked like a pentagon, nice pentagonal shape. Well, the more steps you take, the better it's going to be, so I think 20 would be good. Steps for, I think we took the steps over here too. If we just take 2 steps versus 3 steps, 4 steps, and I think I don't have to go all the way up to 20. You take 10 steps and it looks good already. But still, we have that issue that this thing is not going to cover the bottom part. Still only the top hemisphere. So to get to the bottom of it, we can go to spherical coordinate parameterization, where x is equal to, now, sine phi, cosine theta. Notice I don't have rho. Why not? No. Because rho is 1. So rho is equal to 1 in this case. It's fixed. Now, if we have all 3 variables that we're going to vary, we're actually going to have a solid. Now, we don't want a solid, we just want a surface. And so what you could do is you can fix one of the variables and then see how things change when one of the variables is fixed. So if I have this and then we do our limits all the way around, so remember there's no rho. If you let phi go from 0 to pi and theta go all the way around from 0 to 2 pi, then we can capture that whole sphere. So that would be sine phi. I'll let my phi equal to u. And then my theta equal to v. So phi goes from 0 to pi, and v, which is theta, goes from 0 to 2 pi. So if I graph this, I should see my whole sphere come up. So now it's complete. Okay? Any questions? So if your surface is a sphere, a spherical coordinate system might be good. But there's also something to be said about this graph parameterization, because you can write something in graph parameterization and then eventually turn it into spherical coordinates. So there's a couple ways to approach our next type of integral, which is going to be surface integrals. We're going to be integrating over surfaces, which means we need to parameterize these surfaces. So there's 2 approaches. One, you can go ahead and do the spherical coordinate parameterization of the surface. And when you do that, it can make things a little bit easy for you in describing the surface. But there might be some other overhead that you're going to have to pay for. So that might work. But you can also set your integral up in graph parameterization form and then look at it and say, this is a double integral that I probably want to use a different coordinate system with. And so in that case, you might want to start with the graph parameterization and transform it to polar coordinates. And this is really just, it has two variables, so it'll end up being a double integral that you'll do in polar coordinates. So you can do it like that also. Okay? All right, so I don't know if any of that's making sense yet, since we haven't really dove into surface integrals yet, but we'll do that today. All right, let's take a look at a few more types of graphs. The other things are those quartic section things. Actually, mainly just cones and paraboloids. Why is it that color? So cones and paraboloids, in general, we can look at them as Cartesian or I guess I should draw my arrow down here. We can look at it as in Cartesian coordinates, or we can look at it in polar or cylindrical. So let's start with the paraboloid. If we have the paraboloid, the simple paraboloid z is equal to x squared plus y squared, we could do this in polar coordinates by transforming this into an x is equal to r cosine theta, y is equal to r sine theta, and z is equal to what? R squared. So we want to keep it with just two variables. So cylindrical is like it takes into account the z coordinate, but what we want to do is we want to express things in two variables. So depending on what your limits are, you can have this polar coordinate go higher or lower. So that seems easy enough. Let's take a look at that in our by the way, you can open up another window here. You can go to graph and add a parametric surface, so you can see two parametric surfaces if you want. And then these have labels on top of the window that says parametric surface number 1 and number 2, and as many as you open up. And you can always remove the graph so you can see this one by itself, or you can graph both of them together. All right, so again, we are going to use u and v instead of r and theta, so make your appropriate substitutions. It doesn't really matter which one you do first, because it'll work itself out. So the u is going to be, let's make it go from 0 to 1, and then the v goes from 0 to 2 pi, that's theta. So if we go ahead and take a look at the graph of this, we'll see that it is going to be that parabolic shape. So maybe this is a little bit too much in the r, because r is breaking it up by going outward. So I think I just need like maybe 5 or 10, 8. See it a little bit better. So this is your parabola, and if you change this, if you make this go to 2, then you'll have height 4, it'll grow taller. And if you, what do you think will happen if I change the beginning part, the r, go from 1 to 2 instead of from 0 to 2? What? It'll cut off the bottom part. because you have to look at it from the top, the radial, so this is going to describe some annulus thing. So the radial part, if I cut this off at 1, then I'll cut out the bottom part of the parabola. Right? And of course, if I only take instead of going all the way around to 2 pi, if I only go up to pi, then this is only going to give me the piece of the parabola that's missing. So you can use these things to draw your shapes and create rockets and flashlights and people. Right? Just a bunch of spheres and cylinders and parabolas and cones. So we'll talk about a cone in a minute. So, depending on what your limits are, that's how you can draw your parabola. By the way, if you want to go sideways, in some cases you might, just switch the x or the y. Want to go look at a sideways parabola, you can just say running along the x-axis. So if it's running along the x-axis, then you're going to want the x value to be the u squared. And so this will open up along the x-axis. Right? You can also move the parabola by adding constants to the equation. All right? So this is, I mean, I could do this and I'm having fun, but you really have to be the ones trying things out and moving things around and see, say to yourself that you want to do an upside down parabola that's moved up 3 units that goes right along up against the XY plane, then figure out how to draw that on a graphing program like this.
What about this one above me when we were doing cut up food coins? The cylinder cut off by a foot.
Oh, okay. So that one's not so easy to describe in surface forms, but we'll do it. It gets a little trickier. But before we get there.
I don't actually know how to
Okay. So a cone would be something like this, x squared plus y squared under square root. And so if we approach this kind of like the same way we're approaching the paraboloid and using polar cylindrical coordinates, we can start off with the polar and cylindrical coordinate parts for the x and y. And for the z, just, put in the x squared plus y squared in there. X squared plus y squared is equal to r squared. And so that under square root would be r. And then, of course, if it's going the opposite way, you put a negative sign and do all kinds of stuff. So just to take a quick look at how this thing's going to look like, let's put the instead of u squared, the z will be just r, or u in this case, and you graph it, and then you got yourself a cone. So just imagine now having a cone that's upside down, pointing upward or something. Or, we can also have a cone that's cut open. so that it's only a piece of a cone. Okay. Oh man, wrong page. Okay, so if you have hyperbolic paraboloids or anything else that you can have z by itself, then you can just replace the x with r cosine theta and the y with r sine theta, and then you should be good to go. All right, let's do cylinders next. So cylinders seems like cylindrical coordinates would be the best way to do this. So this idea of graph parameterization won't work anymore. So in cylindrical coordinates, you can draw these cylinders. We can have x equal to, well, r. I'm going to put r here, but I'm going to erase it. Okay, so r cosine theta and y is equal to r sine theta, and z is going to equal to z. Now, if I have all three variables like this, it's not going to work. If I'm talking about a cylinder as a surface, what can you say is not changing? The radius, right? Because the radius is going to be a fixed radius, whatever the radius of the cylinder is. So if I make that radius into whatever the radius is, whether it be 1 or 2 or whatever, now I have two variables, theta and z, to deal with, and I translate that to u and v. Then I would have my cylinder. So let's draw a cylinder on this graphing program. So cosine theta, sine theta, and z. So those are my two variables. I can decide which one's which. And then my v goes from 0 to 2 pi if this is going to be a cylinder that goes all the way around. And my z goes from, let's have it go from 0 to 1. So there's my cylinder. I can go from -1 to 1 to have it go down below the z-axis, because u is like the z, right? What am I going to do? Oh, picture. Cylinder radius 1. I could change the radius, make it radius 2 by just putting in the number 2 here, and then that will give me radius 2. Okay? Yeah.
Will we have to parameter ones, like hyperbolize?
No, maybe, but you guys can figure that out.
Will we still have to use like the axis?
Probably if it has something to do with some circular thing. All right, cylinder gets cut from with a plane. That gets a little trickier. I guess I should do one more. Discs. R and theta. Well, let's see how that goes. Let's do disks first. So for disks, and we're hoping that this is disk that's either it's parallel to one of the coordinate planes, because if it's a slanted disk, it gets a little trickier. It's not impossible, but it gets a little trickier. So let's talk about a disk that's parallel to the XY plane, for example. So a disk is a surface. It's flat, but it's still a surface. So we can let our x equal to r cosine theta and y equal to r sine theta. And then your z, if it's a disk, the z shouldn't change, so the z should just be flat. So let's just say z is equal to 0, and let's take a look at that. I'm going to grab another one. So if I let x equal to u sine v and let y equal to u cosine v. Oh, I did this backwards. Doesn't matter. Spelled it wrong too. Oh, if I'm going to change it, might as well change it. Cosine and sine. And then if I let this just be equal to 0, then I have my polar coordinates spreading out, and then my z value is going to be whatever the z value is. So as the polar coordinates spread out, say from 0 to 1, my r goes from 0 to 1, and my theta goes from 0 to 2 pi. And then my z just lays flat, then it's just going to be a disk. And then if I change my z value to 1, then it would be the same disk, except it goes up 1 unit. Okay, and if I want it sideways, I would just switch one of these variables, the x and the y, or the x and the z, or something like that. Okay? So, for example, if I want to draw a rocket, I would have this as the bottom of my rocket. I would have this as the body of my rocket. And I would have this as the top of my rocket. Now I have a rocket. Okay. To make my rocket longer. I don't know how it's going to go up. That still looks like a house. We need those tails going on the side. Those triangular tails. The fins. Yeah, well, anyways. So you can create surfaces and put them together like this by combining a bunch of surfaces. All right, now that idea of a plane cutting this thing, if we draw a plane, say, this is my cone, this is my disk, so I just want to look at this. If we draw a plane, let's just say 1 minus x minus y. So I need my, wait, this isn't my cylinder. Which one's my cylinder? So if you close it, if you close your windows, you have to open them up again, find them. Is this my cylinder? Nope. Is this my cylinder? Yep, it's my cylinder. So it looks like I might have to let my cylinder go a little bit higher. All right. So let's take a look at this idea of a cylinder cutting a plane. Now, it would be nice if I can just parameterize a surface that would give you the intersection, or that would be inside the intersection of the plane with the cylinder. That would just be inside of the cylinder. And so for that, what we could do is we can do another parameterization of, let's start with a disk. This is my disk, I think. So if we start with a disk, and the radius is going to be 1, so we know the radial distance is going to be 1, except the z is no longer going to be flat. So when z is a constant, you're looking at z is equal to flat. I want the z to be equal to this plane. And so this plane is 1 minus x minus y. Right? So I have my x and I have my y, so if I just say 1 minus my x minus my y, then I should have, and then my r goes to the radial distance, it goes from 0 to 1, then I should have just that circle that has been projected up to that plane. So I'll graph this, and you may not be able to see it yet. Oh yeah, you can kind of see it there. It's in a different form, but it would be even better if we actually take out this graph. So now you see it completely covering that. And then even better if I take out this surface, and you see this is what's left over. Okay, so what we did there was we just look at the polar coordinate. This is a shadow that it would make if it was flat on the xy plane. But you're projecting this disk on the xy plane up onto that plane, and so this is what you have. Okay? Yeah?
So for the disk with the skew plane, what steps should we follow?
The disk with a skew plane like this one?
Yeah.
You would do the disk, except your z would be governed by whatever that surface is.
Okay. Right, but how do you get that z?
That z is the plane.
Right.
So you solve for z. Z is equal to 1 minus x minus y. And then u is equal to r, or x is equal to r cosine theta, y is equal to r sine theta. In fact, you can have this you can have that thing projected up to any surface. And so if we draw the paraboloid, the hyperbolic paraboloid, I think it's x squared, or one version of it would be x squared, and then you put a minus y squared. And then you get a Pringle. I'm just having fun here. Maybe we should just get back to work. All right. So that's the story with surfaces, and that's how you parameterize surfaces. You can parameterize it, and then you have two variables to deal with. So what are we going to do with them? We're going to integrate over these surfaces. Actually have some notes instead of me having to try to write all that stuff. So the way to define surface integrals, they have surface integrals for scalar functions and surface integrals for vector functions, vector fields. And so what I want to do is I want to separate it like line integrals. They had line integrals and they combine two things, the path integral and the line integral. And I'm wanting to separate those two things so that I think we can have a better working definition for these things. Now, there's a lot of interesting geometry and theory behind this, and I kind of just jumped on this definition, or this working definition, to help us compute these integrals. So I don't want to do too much of the geometric theory, although I think it's really, really cool. But maybe I'll do a little bit. I think last time when we were talking about parameterizing surfaces, I talked about going from a UV plane some region in the UV plane, and then sending that to the XYZ space in 3 dimensions. And then I mentioned maybe it was like just a rubber piece of sheet that you can mold and shape into whatever you want to shape it as. And what's interesting about this is that if you partition this, which is what we do generally in calculus, we partition this into little bits of pieces. This also gets partitioned into little bits of pieces on the surface. And I think we saw an example where we went from the XY plane and went directly up. So this is very similar, except we're not necessarily on the XY plane. We can just be on another plane somewhere else that gets mapped into this. And so what we're looking at here, if we blow this up, is a little grid mark over here where we can identify our, change in X, or change in U, and the change in V. And what happens is that gets mapped into a couple of other vectors here. Now, if we want a vector out of this, these vectors are not necessarily going to be the straight lines, or aren't going to be all along the surface, right? They have to lift off of the surface, and so we cross them, and then we find the magnitude of them, and then we get the surface element, the surface area element. So I think we did this work before where we found the surface area. And so this is like the surface area element over here. And the only difference is now we get to put in a function f, a scalar function f, into the integral, and now we're integrating this. So this would be, the application for this would be like a mass and density. If I have a surface that has a certain density at each point, and I know what that formula is, then that formula can go into this integral, and I can say I can use that density function to find the little densities of my surface at each point, and then I would add them all up, and then I would have the mass. So that's your application. Okay? But the way to view this is that we're looking at the cross product of the derivative of the parameterization. So this is your parameterization. You take the derivative, and then you're going to get these tangent vectors on the surface. You cross those tangent vectors, you're going to get a normal vector, but we don't care about the normal vector, or not today yet. But the magnitude of that is actually the area, and that's what we're looking for, is the surface area. Okay, and I want you to think about how this compares. How it compares to the path integral. So compared to the path integral, you're looking at your arc length element, and you're replacing it with the arc length formula. So the surface integral is essentially the same thing, except now you have a ds. It's a capital S. And so the book uses ds for both of these, except they use little s for the length, arc length, and then they use capital S for the surface. So we kind of went our way and decided to use R for the arc length and then S for the surface. So if you look at the surface area problem, it's very similar to the path integral problem. And in fact, speaking of surface area, a special case where the f is equal to 1. We've often talked about this. What happens when the function that you're putting in there is 1? Should be a double integral. Yeah, it'll just be the surface area. By the way, yesterday I think I started off wanting to call these things capital phi. I decided to go back to just calling it R, which is what they do. Okay? All right. Let's do some examples. And then we'll talk more about the special case, because we can tie it in with the rest of the special cases. I have a nice little list of special cases. Example. Do I have an example? Oh, here's the special cases. Density mass. Here's my example. All right, I'm going to do an example. Where we have to find the mass of a thin funnel in the shape of a cone. So from z is equal to 1 to 4. So this is a cone. So that's the next thing that you guys have to be able to do, is you have to be able to look at an equation like this and say, hey, that's a cone. You know, aside from them saying it's a cone, you should be able to look at it and say, hey, that's a cone. That z is equal to the square root of x squared plus y squared. So this is a cone, but it looks like the z goes from 1 to 4. So it looks like it got chopped up here when z is equal to 1 to z is equal to 4. And so we would need to find an appropriate parameterization for that. And then we have a function to put inside of our double integral. So our mass, in terms of writing the formula, is going to equal to a double integral over that surface of this rho function. Okay. It has x and y's and z's in it, but this is a double integral, so I have to be careful about making sure I deal with it correctly. Times the S, capital S, stands for the surface area element. And it all will depend on how we parameterize it. So let's parameterize this. There's a couple ways to parameterize this. One way to parameterize this is to use what's called the graph parameterization. The other way is to use the other parameterization that we were doing, polar coordinate parameterization. Polar? Yeah. So by calling this the graph parameterization, you're keeping the x and y as x and y because you have the graph of this. So your x is going to be equal to x, your y is going to be equal to y, and then your z is going to be equal to this. So initially that doesn't look too bad, but then when you look at the region that you're looking at, the region that you're looking at is going to be the shadow that this thing is going to have on the xy plane. So if you imagine a cone that's been cut off, what's the shadow going to look like on the xy plane? It's a circle with a circle, an annulus. Right? So your domain for your double integral, so the surface integral is essentially going to be changed into a double integral so that we can compute it. And for the double integral, you need a domain. So what we're going to do, I think what I'm going to just have you do is just work things out in the graph parameterization form and then make your appropriate change of variables if you need to. Okay? So here's our parameterization. So our D, of course, we're going to want to go to polar. But we're going to go to polar after we set up the integral. Okay, so let's set up the integral first. Our integral is going to look like this now. It's going to be a double integral, and we're going to integrate over D. So we're going to know that this is a double integral because in the end I'm going to have, instead of a ds, I'm going to have a dA. And a dA is going to be dx dy or dy dx in whatever order. Now the rho on the inside is 10 minus z. Now my dA I just said was going to be dx dy. So my z doesn't work here. What's z equal to? So z is equal to the square root of x squared plus y squared. So that's my 10 minus z function. I left a space over here because according to the formula, I need to figure this out. Right? Does anybody know what that is off the top of their heads? Yeah? Well, close. Let's say this is R. So instead of RU and RV, I'll say RX and RY. So is anybody going to tell me before I start working on this? Well, so Rx is the derivative of each of these things with respect to x. So the derivative of x is the derivative of y is with respect to x, 0. And then the derivative of this thing, whatever that is, I'll say negative. Is it negative? No, it's just positive, I think. That's my guess. So it's 1/2, bring the 1/2 down, x squared plus y squared to the negative 1/2 times the derivative of the inside, which is 2x, The 2 and the 1/2 would cancel, the x would go on top, and then you have the square root of x squared plus y squared in the bottom. This is actually the derivative of z with respect to x, right? Ry, 0, 1, y over the square root of x squared plus y squared, which, by the way, is the derivative of z with respect to y. And then we're going to cross it. Is anybody going to stop me and just tell me what the answer is? We've seen this before. We've seen 1, 0, something, 0, 1, something else. Close? Yeah. That would be the last one, last term. So Rx cross Ry is going to be a cross product vector. It's the first component is going to be negative x squared plus y squared. A second component would be negative and the third component would be 1. Does this look familiar? What?
Taking it a while to get the magnitude.
No. It won't be that easy. I mean, it'll simplify. Oh, maybe it will be. Yeah, because you square that, and it'll be x squared plus y squared. Yeah. And then you want to take the magnitude of this. All right. Do I really have to look it up in our notes? I know, but I'm talking about, what am I talking about? Yeah. Not only that, but we also did, is this the right class? 253? Surface. Back. We did surface integrals already. Open. Get it open. So in the past, we took surface integrals, and the surface integral looked like this. So it's the derivative of f, or derivative of f with respect to x squared, derivative of f with respect to y squared, and then there's a 1 out there. That extra 1 is that 1 that comes up at the end. Anyways, it's there. You can look it up and read through it. But this is going to be a bit messy, and I think if Evan did it correctly, I'll write it out the long way first. I don't know if this is going to be enough space. Negative x over the square root of x squared plus y squared. Squared. Plus y over the square root of x squared plus y squared squared minus 1, or plus 1 squared. So is it square root 2? You guys want to verify that? Yeah?
Think this way, x over x squared plus y squared is 2 times, or square root of x
for, okay, we all agreed? You can work it out. So anyways, that's a constant, and we could take that all the way outside, and then this is dx dy. Now, we still have an issue with this thing, right? So I still am afraid to integrate this with respect to x and y. So let me rewrite this. This square root of 2 that we can just take out. Double integral, and plus our domain D is kind of crazy, right? So I definitely don't want to do x and y here. I want to go polar. So instead of the dx dy business, this is where I go polar, where my polar coordinates now is going to be r from where to where? Is it 0 to 4? What? 1 to 4? Are you sure? Positive 4 or positive sure? Is what? So the z is equal to 4, right? But if you look at the shadow, is it still going to be 4? Is it going to have a radius of 4?
No, not anymore. It'll be the radius.
So it's x squared plus y squared. The square root is equal to 4. I think it's 2. Convince yourselves? Do I need to convince you? Z is equal to 4. Take the square of both sides. Oh, maybe it is 4. Is it 4? I think it's 2. All right, we'll go with 4. So our polar coordinates then will be double integral. It'll be 10 minus r, right? Because it's square root of x squared plus y squared, square root of r squared. Now, whenever we change to polar coordinates, our dx dy is going to come up with an extra r, dr d theta. R goes from 1 to 4, or 2, or 4. And then theta goes from 0 to 2 pi. Okay, so this is manageable. We could do this. And by finding this, you can figure out what the mass is of that thing. Okay. I did give you a quiz because I was planning something different for you for a quiz. And the quiz is going to be on Canvas. So there's going to be 2 quizzes, quiz number 10 and quiz number 11 on Canvas. The first quiz is dependent on that worksheet that you guys got on Monday, Tuesday, whenever you guys had that worksheet. So it'll be related to those problems. The second quiz was going to be related to another worksheet that I was going to give you, but I figured this worksheet kind of needs computer work. And so what I'm going to do is I'm going to have you guys take a look at a worksheet. I'll put this online as well. And have you guys actually do this on the computer. So this uses this computer program that I was using. It's online based. You can download it if you want. You need Java. And then you can plug in these values, which is the values that I plugged in myself. And then I ask you to play around by changing the number of steps and changing some other parameters that make it look interesting. And so these are the cylinders, the spheres that we did. These are the cones and the paraboloids that we did. And the last one are are cylinders, and these are cylinders that may be tilted sideways and stuff like that. So your quiz number 11, the second quiz, will be dependent on this worksheet. So it's not really a worksheet, but this is something that you can play around with, mess around with, and then you can take the quiz. Okay, I think I have the settings set up to 2 tries. What? The quiz will be online on Canvas, and I'll send out an announcement, and I'll have you guys go to the quiz area where you can find the 2 quizzes. Okay? So I was supposed to be up today, but Canvas was down all yesterday, so I'm going to try to work on it today and tomorrow. So it should be up by Friday after Thanksgiving. Yeah.
So when do you want these done?
I want it done before class on Monday. Okay? Happy Thanksgiving. Oh, you guys going to give me the makeups? Is anybody doing the makeups? It's due. I was supposed to be due today.
Wait, what? Oh.
All right, fine.
Are they
It's due on the 1st, whatever.
Wait, so it's due on Monday also?
No, the 1st. What day is the 1st? Thursday. It's due Thursday next week.
So for this weekend, we have all the homeworks up to 16.7 due, including 2 quizzes?
No, 7? Is that what's due?
Yeah, 16 up to 16.7, and then we have 2 quizzes.
Okay, so you have 2 quizzes and your regular homework up to 16.5.
Okay, so 16.6 and 16.7 aren't going to be due on Sunday?
I don't have to look at it.
Yeah.
Which one is which?